We're going to do 3 examples from Stewart's calculus of using the second derivatives test to find local extrema and saddle points of multivariable functions. This video has chapters, so you can skip around the problems as you please. The second derivatives test is outlined here. I'll leave a link in the description to my lesson introducing it, but as you may recall, we need to begin by finding critical points, just like in single variable calculus. The critical points are where the partial derivatives are equal to 0 or do not exist. But of course, this second derivatives test only applies at those points where the partial derivatives exist and equal 0. So we'll find those points and then plug them into the d function and classify them based on these criteria. Let's get into the first problem. We are asked to find the local maximums, minimums, and saddle points of the function. And here it is, f of xy equals, etc. We have to begin by finding the critical points, which means we need to find the partial derivatives, fx and fy. Finding the partial derivative fx, we apply the power rule there for -2, apply the power rule there for -2x, and everything else doesn't have an x, and so its derivative is just 0, since when we differentiate with respect to x, terms without an x are regarded as constants. So fx is just -2 minus 2x, and we're going to set that equal to 0. On the other hand, fy, the partial derivative with respect to y, we apply the power rule to that term to get 4, apply the power rule to this term to get -8y, and everything else has no y, and so its derivative is 0. We set this equal to 0 as well, and we can solve both of these equations to find one value for x and one value for y. If -2 minus 2x equals 0, we can add 2 to both sides to get that -2x equals 2, and so x equals -1. With this equation, we could add 8y to both sides to have that 4 equals 8y, and so y equals 1/2. Also, these functions, these partial derivatives, are defined everywhere, so there's no critical point that comes from the partial derivatives not existing. Hence, the only critical point is the point -1, 1/2, and so it is at this point which we will evaluate the d function. And recall that to evaluate d at a point, we need fxx, the second partial with respect to x, fyy, the second partial with respect to y, and that mixed partial fxy. So let's go ahead and evaluate those. fxx, the second partial with respect to x, is just the derivative of -2 minus 2x with respect to x, which is -2. fyy is the derivative with respect to y of 4 minus 8y, and so that's just -8. The mixed partial fxy or fyx, you could find either one, they will be the same, and we see, of course, that it is 0, because, for example, the derivative of fx with respect to y, well, neither of these terms have a y in it, so that partial derivative is just 0. With all this information, we are prepared to evaluate d at the one critical point, -1, 1/2. fxx and fyy are both constants, -2 and -8, so they actually don't depend on that point. And then we would subtract the mixed partial squared, which is also a constant. So this just ends up being -2 times -8, minus 0 squared, we don't gotta write that. So that's just 16, and so d at this point is positive. Looking back at the test, we know that if d is positive and fxx is negative, then what we have is a local maximum, because fxx being negative implies downward concavity of our three-dimensional surface, and so we have a peak. So since that second partial with respect to x is negative, and of course we could say the same for y, f has a local max of, well, let's plug the point into the function to see what that local maximum is. We see the function here, so all we do is plug in x equals -1 and y equals +1/2, and doing this math, we find it equals 11. And so that is the local maximum of this function at this point. And here's a picture of what that looks like. If we really zoom in and look at x equals -1, that's along this line, and y equals 1/2 is maybe right about there. And if we go straight up, we would arrive at this peak of the surface. Here's our next problem. Again, we'll find the local maximums, local minimums, and saddle points of this function. We have to begin by finding the critical points, and so we find the partial derivatives fx and fy. For fx, we have 3x squared minus 12y, and then this term's derivative is just 0 because with respect to x, it is a constant. Similarly, for fy, we have negative 12x plus 24y squared, and we set both of these equal to 0, because remember, the critical points are where these partial derivatives are undefined, or where they are both 0. Now, these are polynomials, so they're not going to be undefined anywhere, and so we just need to solve for this. And that's just going to take some algebra. From this first equation, setting fx equal to 0, we can add 12y to both sides, and then divide both sides by 12 to get that y is equal to 1/4, that's 3 over 12, x squared. And then from this equation, setting fy equal to 0, we have that negative 12x plus 24y squared, but y is 1/4 x squared, so y squared is actually 1/4 x squared squared. And we're setting that equal to 0. Then, doing the squaring over here, a fourth squared is 1/16. So we have 24 over 16, which we can reduce to 3/2. That's dividing the top and bottom by 8. And then, of course, x squared squared is x to the power 4. Then we can factor an x out of both of these terms, and we can multiply the whole equation by negative 2/3. That way, we get rid of this negative, and we eliminate this fraction. Doing both of those things, we arrive at this equation. X times 8 minus x cubed equals 0. Hence, one possibility, using the zero product property, is that x equals 0. In which case, plugging back into this equation for y, we would have that y equals 0. The other possibility, setting this factor equal to 0, is that x equals the cube root of 8, and so x equals 2. Plugging that back into this equation, we have that y equals 1/4 times 2 squared, or 1/4 of 4, or 1. Hence, our two critical points are 0, 0, and 2, 1. In order to evaluate the d function at both of these points, we're going to need our second partials and mixed partial. So fxx, that's the derivative of this expression with respect to x, which is just 6x. Fyy, the derivative of this guy with respect to y, is just 48y. And then the mixed partial fxy or fyx, find whichever one you like, they are the same. The derivative of fx with respect to y would just be negative 12. With all these pieces in place, we can start to evaluate d. Beginning with the critical point 0, 0, d of 0, 0 is the product of the second partials evaluated at 0, 0, and those are both just 0. And then we have to subtract the square of the mixed partial. The mixed partial is negative 12, that's a constant, and we square that to get positive 144, but of course there is a minus here, so the value of d at this point is negative 144. When d is negative, what we have is a saddle point. So since d of 0, 0 is negative, f has a saddle point at 0, 0, which we'll see in the picture in a minute. Evaluating d at the other critical point, 2, 1, is a little bit more work. The second partial of f with respect to x at 2, 1 is just 6 times 2, or 12. The second partial with respect to y evaluated at 2, 1 is just 48 times 1, so 48. Then again, we subtract the mixed partial squared, so we subtract 144. This ends up being 432. So d is positive. Also, the second partial with respect to x is positive. And so that implies what we have is an extreme value, and the surface is concave up here, so we have a minimum. What is that minimum? Well, we just have to plug in that critical point, 2, 1, into the function. This is the function for your recollection, so then just scrolling all the way back down to our evaluation, the function's value at 2, 1 is 2 cubed minus 12 times 2 times 1 plus 8 times 1 cubed. This ends up being -8, and so that's the minimum value at this point, 2, 1. That is a local minimum. Here is a picture of the surface. If we trace along the line, you can see at x equals 0, y equals 0. If we go straight up, you can kind of see how we've got a saddle point on the surface there. Meanwhile, if we go to x equals 2 and y equals 1, that's going to be right over here. And then if we go straight up, you can kind of see how we've got a minimum there. It's like at the bottom of a valley of this surface. Our last example is a nice easy one. We're asked to find the local max, local min, and saddle points of this function. We would again begin by taking the partial derivatives. Fx would just be e to the x times the constant cosine y. And fy would just be, well, the derivative of cosine y is negative sine y, and then you have to multiply by the constant e to the x. So those are the two partial derivatives, which we would set equal to 0. But for both of these to be true, since e to the x never equals 0, we would need a single y value such that cosine y is 0, while sine y is also 0. And that's not possible. There's no angle where sine and cosine are simultaneously 0. Hence, there are no critical points of this function. Of course, these functions exist everywhere, so we can't find a place where the partial derivatives are undefined. So yeah, this function f of xy has no local extreme values because there are no critical points. Here's a graph of the surface. You can see as x gets negative, the surface just totally flattens out to 0, because when x is getting negative, we're having e to a big negative power. So we're actually dividing the cosine function by some big number, so it just flattens out in that direction. But those are a few examples of using the second derivatives test to find local extrema and saddle points of multivariable functions. Let me know in the comments if you have any questions, and be sure to check out my Calculus 3 course and Calculus 3 exercises playlists in the description for more. Thanks for watching.
Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about. Stressed out, honey, I've been stressed out lately. Don't know what's what, don't know what I'm stressed about. Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about.